So I think first I want to thank the organizers for the invitation, and I apologize I cannot be there, just too complicated. So I wish lots of background noise. I don't know where they come from. Okay, I wish I'm in Paris give this talk on Koo-Saleur formula rather than in Santa Barbara in my office. So I will talk about Koo-Saleur formulas, and I came to these formulas from a totally different kind of a motivation. So most of my talk will be very speculative. So it's more like a different motivation than any technical things. So I ran into Koo-Saleur formula through something called the quantum Church-Turing thesis. So this is basically a belief or a philosophy. If you think about computation, we have classical computation. But if you think about quantum computation, you just want to add quantum to computation. And the belief for many people is there's only one possible mode of a computation for quantum. So if you believe this, and then that means quantum field theory won't give you anything new. So that implicitly implies that any physical quantum field theory can be efficiently simulated by quantum computers. So that's basically the question I'm interested in. And in particularly, I'm interested, if that's the case, how do we simulate conformal field theories? So by conformal field theory, my talk will be all unitary, two-dimensional, rational. It could be chiral and it could be full. So, but most of the time will be chiral conformal field theories. And I want to start with some generalities. So in principle, if you think about computing, if you give me any physical theory, there would be a computational model. So the idea is the following. It's very general. I think it's probably known to Turing already. So if you have a physical theory, if you think about a computing problem, so a computing problem, just a family of functions you want to compute. So if you have a function, you want to compute the value, you can imagine when you give the input, you already have a physical theory. So you just write the input as a state of your physical theory. And then the calculation is done by evolution of your theory. And then the answer you hope would be given by the final state of the evolution. So if you think this way, then you can put any physical theory into the box. If you put in classical physics, that's the Turing machine. If you put in quantum mechanics, that's exactly quantum computing. And the question I'm interested in is, if you put in quantum field theory, do you get anything new? And most people believe there's nothing there. So it's the same thing as quantum mechanics. So since I'm a mathematician, so I want to do things rigorously, and there are not many classes of quantum field theories which mathematicians can understand or have a definition. And two large classes I know of are topological quantum field theories and conformal field theories. So the first time I thought about quantum computing actually is to prove the theorem with Michael Friedman and Lex Kitaev around year 2000, which is if you put in topological quantum field theories into the box, you get nothing new. So that's exactly quantum computing. So that's actually how we get into topological quantum computing in another way. And all I want to do is, what about conformal field theories? And I have to say, I don't have any answers here, mainly speculations and motivations. And the main difficulty actually is the obvious one. What do you mean? So it's the formulation of the problem, which is very difficult. It's not necessarily the technical proof. So the first question would be, when you say simulate quantum field theory, what do you mean? So I don't know exactly, but there are at least two things I want to think about. One are the unitary evolutions, and the other are the partition functions. So you basically want to simulate the evolution efficiently, and you want to approximate the partition functions efficiently. And as I said, the thing which I know really well are topological quantum field theories. So I will start tell you about the story about topological quantum field theories, and then use that as things to motivate conformal field theories. So in topological quantum field theories, the evolution are given by representations of a mapping class groups. In particular, I want to focus on the braid groups. And for the partition functions, there are three manifold invariants, and in particular, I will focus on the link invariants. So if you think about topological quantum field theories, they are really the T can also mean trivial. So topological quantum field theory, the kind of a trivial quantum field theories in the sense the Hilbert spaces which appeared in the theory are finite dimensional. And that makes things much easier because in quantum computation, you are using only finite dimensional Hilbert spaces. And the main difficulty is in quantum computation, you have a tensor decomposition of the Hilbert space into qubits. And in topological quantum field theory, they have no intrinsic tensor product. So that's actually pretty much the main difficulty. And then another advantage of topological quantum field theories are the mapping class groups and the braid groups. They have some obvious generators, and you can consider that as local generators. And we have these generators, and then you can obviously think about the complexity of a mapping class, just how long you have to write this mapping class in terms of the generators. And a key ingredient in the simulation of a topological quantum field theory is given by some kind of locality. So this is given by the gluing formulas. So basically means that if you want to know a state or a surface, I'm talking about 2+1 topological quantum field theory, and they can cut the surface into pair of pans, and then the state can be recovered from the states on the pair of pans. So these three ingredients make the simulation of topological quantum field theory relatively easy. And if we can see later on, those are all very difficult problems for conformal field theories. And I will quickly go over the idea of simulation for topological quantum field theories because this is the only mathematical simulation I know of well. And basically, I want to do everything modeled on this simulation. So suppose you have a repetition of the braid group you want to simulate. And in computer science, when you say I have a problem, you have to have a parameter because you need the parameter to go to infinity in order for you to say what is efficient, what is not efficient. So here the parameter is the number of strands in the braid group. So you have a representation of the braid group acting on some finite dimensional Hilbert space Vn. And you say, I want to simulate this by a quantum computer. So a quantum computer just means you have a sequence of Hilbert spaces which decompose into usually is a qubit, a two-dimensional Hilbert space. But that's completely a convenience. Any finite dimensional Hilbert space will do. So you take a tensor product of many so-called qubits, and then you build a quantum circuit, which is just some small gate, which means it's a unitary which acting on one or two or three tensor factors, and then you just compose them, and that's called a quantum circuit. So if you want to simulate a unitary of a braid group representation rho, as in the diagram below, and you hope that you can embed your Hilbert space Vn into a tensor product of QDs, and you want this embedding to efficiently so that this diagram commute. So that means if you want to run the rho, you just run the quantum circuit. Because it's commute, and then everything you want to know about rho can be deduced from the circuit. And there are many difficulties, like rarely this really commute in TQFT. So there are errors, but more or less you take care of all the approximations, all the efficient embeddings, and the complexity. You can find this diagram for topological quantum field theories. And if you want to approximate the linking invariance, and basically what you do is what people normally call topological quantum computing. So I already said in the last slide that the braid representation can be simulated by a quantum computer. So basically you run this physical process, and then the quantum computer on the other side, the simulation would do the calculation or the approximation of linking invariance. So physically, you just create anyons from the vacuum, and then you braid them, and then you annihilate. And we annihilate, they sometimes go back to the vacuum and sometimes their particle come out. So what you do is just you repeat this process polynomial many times in the input, and you just recorded the probability when you annihilate the particles, they go back to the vacuum. And then this probability will approximate the linking invariance of the link which I draw and the absolute value. And there's some subtlety about what kind of approximation. So there's some normalization involved, and that's a subtle things I won't really talk about. So basically, this is how we do for the simulation of topological quantum field theories for the mapping classical representation and the approximation of the linking invariance. So now the question I'm interested for the last few years is, can we or how to extend this to conformal field theories? And besides, the so-called church thesis, that's not any evidence, that's just a belief. And there's one small piece of evidence that it might be simulable for conformal field theories. And the reason is in topological phase of matter, that is a bulk edge correspondence. And the conformal field theory just sitting on the edge of a topological phase of matter. A topological phase of matter, the bulk is described by topological quantum field theory, and the edge is a conformal field theory, a chiral conformal field theory. So therefore, in a sense, to simulate conformal field theories is more or less the same as to simulate this bulk edge correspondence. If this bulk edge correspondence is efficient, and then in principle, you can believe you can efficiently simulate conformal field theories by transport whatever you know about topological quantum field theories from the bulk to the boundary. So this is kind of some evidence. And so now I want to really, this is, as I said very early, very speculative because I don't have anything really definite as topological quantum field theories. So there are two analog things I want to simulate. One is the analog of a mapping class groups. And that's actually, I consider to be the representations of the diffeomorphic group of the circle acting on the Hilbert space of states for conformal field theory. And then we also want to approximate correlation functions. And this is kind of the analog of linking invariance. And now you can see there's some obvious problem now. So first, as I said in topological quantum field theory, we have a finite dimensional Hilbert spaces. Now the representation of the diffeomorphic group is infinite dimensional. And the infinite dimensional is very difficult to deal with for quantum computers, because quantum computer is a bunch of qubits, just linear algebra in finite dimension. And the other one is the diffeomorphic group. There are no obviously so-called local generating set. It's very difficult to say, oh, what's the complexity of a diffeomorphic S1 if you don't have a obvious generating set. And the other one is locality. All quantum field theory are supposed to have some kind of locality, but how to formulate this for conformal field theories, I really don't know a good way for to help me for simulation. And also, there's a big difference between topological quantum field theory and the conformal field theories. Topological quantum field theories, they are universal properties for gapped quantum systems. And the conformal field theories are for gapless ones. So they are also fundamentally different in this sense. So as I said, I want to think about simulation of conformal field theories, but I don't have much definite to say. So that's basically I want to start with. And so here's one analogy I want to make. So since the Hilbert space of conformal field theories are infinite dimensional, we have to approximate it by finite dimensional Hilbert spaces, because that's how quantum computer work. And one analogy I want to make is, if you think about the diffeomorphic group S1, maybe we can consider this as an analog of the infinite braid groups. And then the one mathematical definition of a chiral conformal field theory is a vertex orbital algebra. And that's kind of like a limit of the representation space of the braid groups. And then you can ask the question, what's the analog of our braiding? And how do we approximate a vertex orbital algebra, a chiral conformal field theory? And the naive obvious thing is just truncated the vertex orbital algebra into VN. That's the energy truncation. But this is not a very good one because one of the things we want to simulate is related to the Virasoro generator LM, and they will become 0 for most of this. So that's not a very good approximation. So the one I'm thinking about right now is basically the kind of Hilbert space for the representation of the braid group. It's not clear yet how the VOA are related to these Hilbert spaces, but it will become clear later on when I talk about anyonic chains. And then the other analog I'm looking for is what is a braiding in terms of chiral conformal field theory. And that's like the punchline, what I want to talk about today. I want to say this is more or less a version of Koo-Saleur formula. So to kind of try to convince you this is not too wrong, so let me make some analogy again. So let's think about the relation between template algebras and the braid groups. And if you think about the Kaufman bracket, this is actually just a picture of a formula Wang Jones already wrote down in his famous paper. So we can really think about the braid group kind of some kind of Lie group, and the template algebra is kind of some Lie algebra. But actually we know they are related in a very precise way. Template algebra actually are quotient of the group algebra of the braid group. But I want to think more loosely in terms of the algebra and the Lie group. And now we think about vertex operator algebra, and actually there are at least 2 mathematical definitions of chiral conformal field theories. One is the vertex operator algebra, and the other is a local conformal net, which coming from algebraic quantum field theories. So if you think of these 2 approach of chiral conformal field theories, it definitely should be equivalent, although we don't know for sure, but at least for minimal models, there's a mathematical theorem that they are the same. So I want to think of the local conformal net definition of chiral conformal field theory as the Lie group version. And I want to think about the vertex of the algebra definition as the Lie algebra. So both definitions have pro and cons. So in vertex of the algebra, we have the obvious notion of what is a quantum field. And in local conformal net, we have a very difficult time to figure out what is a quantum field in there. But on the other hand, local conformal net are given by bounded operators, and the vertex operator algebra are given by unbounded operators. So we all know how hard it is to work with unbounded operators. So the analog of a braid, I basically want to claim they are roughly like exponential of the Virasoro generators. So I couldn't really simulate or know how to simulate the diffeomorphic group representation, but I want to think about a subgroup, which is you take the smeared conformal field. So the smeared conformal field is defined by take any function on the circle, you expand into Fourier expansion, and then you form this linear combination of the Virasoro generators. And in order for me to think about finite simulation, I want to think about functions with Fourier coefficient only finite, many non-zero. And then if I form this smeared field and I can exponential it, and then it's a deep theorem of Goodman and Wallach that representations of those subalgebra in the Virasoro can be integrated to continuous representation of a diffeomorphism of S1. And I think for those who think about, we all know how hard it is for non-compact group to integrate to the Lie group. So the very good connection between representation of Lie algebra and the Lie group is lost when you go to non-compact or infinite dimensional. So, but for this special smeared conformal field, you do have a very good connection. So that's really I want to consider as to address what's the complexity of a diffeomorphic group S1, and that's the kind of algorithmic part of the diffeomorphic group. And if you think this way, you won't miss it. The obvious thing to think would be if we approximate the vertex operator algebra by finite dimensional Hilbert spaces, and then we want to know how the Virasoro generators look on the finite dimensional approximations. And the Hilbert space given before actually just anyons, and then you want this approximate the vertex orbital algebra. And if you think about braid group, as I already mentioned, the important thing is they related to template algebras. And the template algebra generator, actually, they are kind of like a final version of the Virasoro generators, except that there's a duality here. The template algebra live on the real space, and the Virasoro generator is given in terms of the energy basis. So there's a Fourier transform happening here. So then basically the mathematical question I'm interested in is, what is the Virasoro generator restricted to the real space of anyons? And if you think about scaling limit, there was a talk last one. Unfortunately, the online didn't work out. So you want to take a scaling limit, and it turns out the template algebra is kind of limiting to the conformal field. And so you can see that a local template generator is really non-local in the energy basis. I think this is a difficulty in the simulation, which is we have two local bases. And the vertex orbital algebra is defined in terms of the local energy basis, but the finite dimensional approximation using template generators is in the real space. So we have a duality here. And then basically I want to say that the analog of a braiding for vertex orbital algebra in the energy basis is basically exponential of a finite truncation of the Virasoro generators, which this is what we know as Koo-Saleur formulas. And as far as I know, of course, I didn't know the history very well, but the reference I knew was this famous paper by Koo-Saleur now, which they give the spin chain version, which can easily turn into a template of the finite truncation of the Virasoro generators. And there's a beautiful numerical simulation recently by Linear and people list below that this formula seems to work really well, first discovered by Vidal and other people. But there is a small problem, which is it seems that there's something not quite right for the central charge. And the latest simulation says the problem seems to be systematic. It's only affect the cubic term in the formula for the central charge. So I don't know this is a deep problem or this is just some technical thing. So personally, I think there's something conceptually deep in this problem, which is how do we write the Virasoro generators on a finite lattice in real space? And so that's what I want to say now. I want to be a little bit more specific about how to re-examine this Koo-Saleur formula in terms of the language I'm familiar with anyonic chains. So the anyonic chain language is basically the following. So suppose you have n anyons in a disk. And then we know anyons are the universal property are given by topological quantum field theories. So if you're given a boundary condition on the disk, and then there's a Hilbert space for this n anyons. And the Hilbert space has many bases. And one is that you just choose a fusion tree, and then you have all the admissible labelings of the fusion tree, and that's one basis of this Hilbert space. And then you can write down Hamiltonian for the interacting of the anyons by take any two adjacent anyons, fuse them, and they will either go back to the ground state or there's some other outcome. And you just penalize the non-vacuum outcome. So you want the ground state to be the fusion of every adjacent anion go back to the ground state. And of course, you fix the anion type. All the red dots are the same species of anion. And you write down this projector Hamiltonian, and you can see this can be rewritten using the template generators EI with some normalization. And I want to draw the, actually this is a conformal block. I want to draw the fusion tree into a semicircle because I want to make a connection to conformal field theory. And the anyonic chain, actually, if you want to conceptually think about this, when way back by Wang Jones, he thought about vectorization of braid groups. And Station Q wrote a paper, very explicit study, the golden chain, which is the anyonic chain for Fibonacci anyons. And we observed a few things. One is that you can map this into a standard statistical mechanics model. So you can deduce from there it's exactly solvable. And then we did extensive numerical simulation shows that the golden chain, which is the anyonic chain for Fibonacci anyons, should converge to the tri-critical conformal field theory minimum model of central charge 7/10. And the reason this is a stable thing is that there are topological symmetries which protect the gapless of the limit. And if you think this way, actually, my student Moji and I kind of come up with a slightly different formula than Koo-Saleur. So I won't, the font are really small, some formulas, actually, you're not supposed to read them anymore. I just showed there's something and they see the reference. So we started with try to read kind of back, reverse engineering, what kind of finite lattice approximation of the Virasoro generators. And we came up with something very similar to Koo-Saleur, except in the Koo-Saleur formula, there's an index j plus 1, and we kind of used the 1 j plus 1/2. So there's a shifting of a half lattice site. And the reason there's a shifting is that we set the coefficient and try to calculate the commutator. And the commutator of commutators, we want to study the convergence of algebras. And it turns out this 1/2 works slightly better than j plus 1. And if you think about what that means, is that you want to think about the template generator is sitting within two sides rather than sitting on a side. And I think Hubert convinced me our formula is not any better than their formula conceptually. I think we will have the same problem about the round central charge, but I think numerically, they probably convert a little bit faster because there are fewer high energy and low energy mixing. So, so that's actually basically I ran into this famous Koo-Saleur formulas. And now I want to, as a mathematician, I want to do everything mathematically. So we want to ask you, in what sense this finite approximation really converts to conformal field theories? And so my student and I, we try to come up with a mathematical definition, and it's more or less, it's just a mathematical formalization of something earlier done by Azad, Nick, and Hubert, and in some of their papers on spin chains. And also, I'm more inspired by the numerical simulation we did on anyonic chains. So the idea is basically to take the slogan that quantum field theories are low energy effective theory seriously, that when you have a quantum system on the spin chain, you want to diagonalize the Hamiltonian and then separate all the states into different energies, and then you want to converge energy by energy. So formally what you do is you take a cutoff of the energy, you take a limit fixing this energy, and then you let energy goes to infinity. So it's a double co-limit construction. And this is more or less what did in the work of Azad, Nick, and Hubert on spin chains too. And then using this mathematical definition, and we can prove this at least for the Ising anyons. And this is, as many people know, that you can rewrite the Ising anyon using Majorana operators. So that's the Hamiltonian looks like. And then just fit into, as I said, you are not supposed to read all the small font things. It's just to tell there's something in the paper. And then we can, I think I would say a larger portion of the work is done by people in this community, in particular Paul Findlay, that we just formalize everything And then we can prove, at least for the Ising anyonic chain, they converge with the right boundary condition to both the vertex operator algebra and the local conformal net. So they converge in both senses to the right conformal field theories, which is M43 minimal model. And my student afterwards, Moji, wrote a thesis on this topic. So he progressed much more than in our paper. So he also have some partial result. Again, as I said, you're not supposed to read the small font. And basically what I want to say is that he wrote a thesis. There's some simulation of partial result on both the simulation of the unitary evolution and the approximation of the correlation functions. And also, as I said, it's a very difficult problem to formulate. And we are definitely not claiming this is the definite formulation or the right formulation. It's just something to start with. And finally, I want to say that it's really my dream to go beyond Ising chain, which is the golden chain, the Fibonacci chain. So this is, I have no doubt, the Fibonacci chain would convert to the tricritical minimal model of central chart 7/10. And there's the low panel is the numerical simulation. And also in the paper I have with Moji, we basically abstract out all the conditions which is sufficient for us to prove that the Fibonacci chain would converge. Unfortunately, we couldn't verify all the conditions. For example, one thing I'm thinking, I asked Paul Findlay a few days ago, is if the exactly solution in the statistical mechanics correspondence would tell me about the spectrum of the Fibonacci chains, so that I know, how the eigenenergy level or the eigenvalue converge, and then how the states converge. So we don't know how to do this, and I really want to think about this very challenging case of the golden chain. And finally, I want to say to Hubert, thank you, happy birthday for the occasion, and I wish not only you have time to enjoy the beautiful mathematical physics, and also you find time to enjoy some other beautiful things in life, such as the Great Wall of China, and also a fine glass of champagne. Thanks for listening, and I will stop here.
Thank you. So, Hubert.
Should I stop sharing?
No, hello, Zhenghan. This is Hubert. Sorry, you can't see us, I guess.
If you stop sharing, we can see you better.
Do you hear me? Zhenghan, do you hear me? I don't think he hears us.
Zhenghan, can you hear me? What? I can't see. Oh, okay, yeah, here, yes. Okay, it's can't see anything. Where's my arrow? Oh, now I'm here. There are three connected.
You had it, yeah.
Okay, Zhenghan, can you hear me now?
Yes, I can now.
Okay, if you stop screen sharing, we can see you much better, because now your likelihood is very small. Okay, so I'll hand the micro. This is Jesper. I hand the micro to Hubert.
Sure, thanks.
Hello, Zhenghan, that's me. Thank you for the champagne. I haven't drunk it yet. Yeah.
Oh,
so
great.
thank you for the nice talk. So we've tried to play with our generators by shifting +1, +0.5 for the Fibonacci. I don't think it, is it the Fibonacci or the golden chain? Anyway, it hasn't made much of a difference.
Oh,
Yeah, no, it doesn't seem to be that simple. But what I was wondering was these conditions you mentioned on
yeah.
the last slide, are they're
Yeah.
not necessary, they're only sufficient conditions. Am I correct?
Yes, yes. It's just that we abstract out from the Ising chain. There's nothing we can say about necessity. Just if you have those, you will just the same proof will go through, but probably it's too
Okay.
strong.
But well, you're saying so these are things we could check with the better ansatz maybe, or
Yeah, that would be great. That's one
yeah.
thing. I have to admit, I have never learned properly the beta enzyme and also the correspondence between the correspondence of 1+1 quantum and the 2+0 statistical mechanics.
Right.
And I think I'm starting to think about to get exactly numbers in statistical mechanics, so I can see some prediction.
Okay, well, we'll talk about it. Okay, thank you again. Huh?
Sure.
So, any other questions? Yeah.
Hi, it's Linnea. No, just not a question, just a comment that this whole issue with the central term, it's not really a problem if you take the scaling limit properly, like you were talking about with putting a cutoff on the energy and taking the double limit the correct way. So I'm not sure there's actually something deep. And that, yes.
Oh, really?
Yeah, and in the examples that I have seen, then indeed your version with just +1/2, it does converge faster. So I think it's slightly better, but it doesn't really change the qualitative features.
Yeah, that's what I was saying too. But I'm a little bit surprised you say that maybe I shouldn't think too much about the central chart thing, because I thought there's something. Well, I can tell you what I'm thinking. So I'm thinking about lattice models and continuum theory in at least two different contexts. One is anyonic chains or spin chains, and the other is so-called fractons of some very exotic lattice system. And I consider it's difficult, and I hope it's a deep question, which is what's the symmetries in the continuum and the symmetries on the lattice, how they corresponding to each other. I don't think they correspond very well. You can have accidental symmetry in the continuum. So I think anyonic chains seem to be a very good place to look exactly, the correspondence. So hoping the central chart is something, tell us something deep about this correspondence. Maybe it's not, maybe just some cutoff thing. Anyway,
Yeah,
so
I'm not sure if it's not something deep. All I can say is that if you take the limits in the proper order, then the effect goes away.
you mean if you take the order properly, then you can also get the cubic term correctly?
If you set the system size to infinity first and then you raise the energy cutoff, then it's fine. But if you do it in the opposite order, then you get this wrong central term.
Okay, maybe that's already something interesting. So it depends subtly on how you take the limit, right?
Exactly. It really depends on the order of the limits.
Okay, thanks.
Hi, I had a more basic question. So it's about the simulation of CFTs. So at a very modest level, this question has somewhat been addressed for lattice models which realize CFTs in the continuum limit with tensor networks. And what was observed was that the question's answer depends on the operator. If you want to imagine simulating the operator dynamics in the Heisenberg picture, and then it matters if you have if you imagine the transverse field Ising model, it would matter if you look at an operator which is, let's say, sigma z or sigma x. So I was wondering, in your scheme of efficient simulation of CFTs, are you imagining a scheme which is efficient for everything, or is it something that will also have a potentially similar feature?
I'm aware of one paper about tensor network, but that I know is more like a classical thing to write, but To answer your question, I definitely want a simulation which is uniform. It shouldn't depend on, what's the particular operator or something. One thing I find it hard to work with for, transfer matrices and statistical mechanics is that unitarity is very hard to implement because, there, I don't know, it's maybe just, I'm not good enough to think this through. So I definitely, just quickly to answer, I definitely, the hope, that the scheme should be a uniform simulation. Of course, uniform in the sense, the operator has to have a hierarchy. They should have a parameter, which means how local they are. And then the efficiency depends on the locality, quantity. But if they have the same locality, they should be simulated uniformly, not, one particular one. So I hope that's answered your question.
All right, so we are going to stop there. So let's thank Zhenghan WANG again.
Thank you.